Hello everyone and welcome back. Now, as I promised, starting from this video, we are going to look at different types of sequences. Particularly in this video, we are going to look at sequences that looks like a rational function. Sequences where the general term of the sequence look like a rational function. For example, here, what is a rational function? A polynomial over a polynomial, like this example that I have given here. Now, if you want to decide the convergence and divergence of this sequence, you have to take the limit, right? We know that for sure now. When n goes to infinity, we have to take the limit of this function. Alright, now how do we find the limit of a rational function that look like a rational function? Now, forget about this for a moment, okay? Let us take this numerator, 2n square plus 3n plus 5. Okay, on a second thought, I'm going to write it as 2x square plus 3x plus 5. I'm going to write it as a function. It's just the same numerator, I just replaced n by x. Let's try to think it as a function. Now, this is a polynomial. Now, we want to look at the behavior of this polynomial eventually, or for large values of n, or that means for large values of x, right? Now, if you think about this, when x goes to infinity or when n goes to infinity, the numerator is definitely large, right? It's getting huge. And the denominator also, n square plus 1, that's also getting large, right? I mean, n square plus 1, million square plus 1 is extremely huge. Billion square plus 1 is extremely huge, right? So when you keep on plugging large numbers of x, both numerator and denominator get large, right? So it's infinity over infinity. So it gives you an indeterminate form, because infinity over infinity is not something defined in mathematics, okay? That's undefined, okay? That's an indeterminate form. So what this means is that there's a trick. Okay, that's not the real limit. Infinity over infinity is not the real limit. We have to find the real limit, and it's hidden here somewhere. So we have to use a special trick. So that's what I'm going to do. I'm going to teach you this special trick. Now, if you go back to this polynomial, we're looking at the end behavior of the polynomial, eventual behavior of the polynomial. That means what happens to this polynomial when x is large. Now, here's the thing. When x is large, even though we have three terms in this polynomial like 2x square and 3x and 5, not all those terms going to matter when x is equal to large. When x is equal to large, there's a dominating term. That means when x is equal to large, I say 2x square will take over this polynomial. Okay, I say 2x square is the dominating term of this polynomial. That means, in other words, when for large x values, the polynomial 2x square plus 3x plus 5 will look like just 2x square. Okay, and we can drop 3x and 5. How come? Now think about this. For example, think about when x is equal to 1000. When x is equal to 1000, x square is like what? Million. 2x square is 2 million. So this is 2 million. 3 times 1000 is 3005. So these two together will give you 3500. This is 2 million. See the difference? Very different, right? Almost these two terms, they are neglectable, right? What's 3500 compared to 2 million? Now think about, I just plugged 1000. Think about plugging even large numbers, okay? So for every polynomial, there will be a dominating term. Okay, again I'm saying this polynomial for large x values will look like 2x square. If you don't believe me, let's look at some pictures. Alright, so as I said, let's use Mathematica to see what's going on with this dominating term idea. Right, so in the Mathematica, I have this function 2x square plus 3x plus 5, which is the function polynomial that we have been talking about. And I claimed its dominating term is 2x square. Let's try to plot these two functions simultaneously. Okay, so I'm going to plot it. Now, the blue color curve is 2x square plus 3x plus 5. The yellow color, orange color type of curve is 2x square. Now, as you can see, the two functions are totally different, right? But now I am drawing this function for x values between 0 and 10. So this is in the beginning. Now let's try to draw these two functions, okay, for large x values, because we are talking what happens eventually, right, for large x values. That's what I said. When x is equal to large, these two polynomials that are here, 2x square plus 3x plus 5 and 2x square, they are almost the same thing, okay, or we can neglect 3x and 5. So let's see. Let's try to draw these two functions for x values. I don't know, 1000 to 1 2 3 4. Okay, now you can see there's hardly any difference. Right now, if I zoom in here furthermore, I would be able to see a difference, but they are almost the same thing. Almost the same thing. They're not going to be the same thing ever, because 3x plus 5 is technically there, but the difference is so small, or 3x plus 5 is almost neglectable. Okay, it's neglectable. So as you can see, for large x values, there's hardly any difference between these two functions. Okay, so the simple idea is that for large x values in a polynomial, the term with the highest degree, that's the dominating term, or the polynomial will start to behave just like the dominating term, and the rest of the terms can be neglectable. Okay, all right, so let's go back to our old sheets. Okay, now hopefully I have convinced you through pictures about dominating term. So what this means is that for this rational function, for large n values in the numerator, what matters is 2n squared. That's the term that matters. In the denominator, if you think about this polynomial separately, n squared plus 1, the term that's matter, the dominating term, is n squared. I mean, what's 1 compared to n squared? Think n is large, right? Okay. So n square is the dominating term, right? So now think, for large n values, so taking the limit of this rational function is same as taking the limit of this simplified version of this rational function. Okay, simplified version means this new version only contains the dominating terms. Okay, I can say almost equal. Okay, not equal, almost equal, because technically it's not the same thing, but almost same thing. Now you can see the nice thing about this is that n square cancel out. When you're just dealing with the dominating term, certain terms simplifies out, and what's left, it's just you are left with 2, right? So it's all about taking the limit of 2 when n goes to infinity. So what is it? It's 2. So really the limit of this rational function, okay, when n goes to infinity, is actually 2. It's not infinity over infinity. Now, this happens when you only look at the dominating terms. Okay, you get this answer if you look at the dominating term. And that's what you do when you have sequences that are made out of rational functions. And when you want to take the limit, look at the dominating term of the sequence. Right, now you might ask, well, how do you find the dominating term? Okay, so the way you find the dominating term of a given polynomial is take the term with the highest degree, highest power of the variable. So in this polynomial, variable is n, highest power is n squared, that's the dominating term. Here, the variable is x o n, n square is the highest power, that's the dominating term. Okay, so let me give you another example. So another example is sequence 2n cube plus 1 over 2 n square plus 1. Okay, this is the second example. Okay, n values are going from 1 to infinity. Now you want to take the limit. So when n goes to infinity, this is 2n cube plus 1 over n square plus 1. Okay, so what's the dominating term of the numerator? So the dominating term of the numerator is 2n cube, right? Take with the coefficient, okay, 2n cube. Now the dominating term in the denominator is just n square, right? Think them independently. Don't try to think about dominating terms of numerator and denominator at once. Treat them as two separate polynomials and find the dominating terms separately, individually. Okay, now you can simplify what's going on here. So n goes to infinity, n square and n cube cancel out and leave us with 2n. That's okay. So what's the limit of 2n when n goes to infinity? Well, it's infinity. Okay, no way around that. 2n gets large when n goes to infinity. So the limit of this sequence is actually infinity when n goes to infinity. So this is a divergent sequence. Oops, I forget about the first sequence to mention the convergence or divergence. This is a convergent sequence, right? The first example, because the limit is finite, limit is to finite number, so it's convergent. Okay, right. And let me take another example. The third sequence is 2n square plus 1 n cube plus 1. So let's take the limit. Limit when n goes to infinity, 2n square plus 1 divided by n cube plus 1. Now this is almost same as taking the limit of the dominating terms of both numerator and denominator. The dominating term of the numerator is 2n square, right? The term with the highest power of n. In the denominator, it's n cube. Think individually, okay? Now n square and n cube cancel out. What do we get? We get 2 over n will be left on the denominator, right? Right. Now when n goes to infinity, denominator gets large, but 2 over n overall gets small and goes to 0. So the limit is 0 of the sequence when n goes to infinity. So this third sequence is convergent, right? Because 0 is a finite real number. Okay, so that's how you find the limit when you have a sequence that's represented as a rational function. You look at the dominating terms of both numerator and denominator. Right, one more thing before we finish this video. I want to show you how another way you can find the limit of a rational function. Now let's go back to the first example. So the sequence is 2n square plus 3n plus 5 over n square plus 1. Now the idea where you think about the dominating term, you can use it as a shortcut, okay, to find the limit, okay, or scratcher. But here's how you can do this properly. So when you want to take the limit, okay, of a rational function, what I recommend you to do is, now again, same as the dominating term idea, in numerator and denominator separately factor out the highest power term. Okay, right. So in the numerator, the term with the highest power is 2n square. So just factor out to n square. Just leave 2 inside. Don't take 2 out. Just factor n square. Okay. Now when you factor n square, when you take n square from 2n square, 2 will be left. Plus, when you factor n square, you have to divide 3n by n square. Okay. Plus, when you take n square out, so you have to divide 5 by n square. Okay. Right. Now, in the denominator also, just take out the highest degree term. So, n square is the highest term with the highest power. So, take that out. So, when you take n square out, there will be 1 here and 1 over n square, because there was no n square here. So, you have to divide by n square. Now what you can see, you can cancel out, simplify the terms that you factor out. Right. Now let's see what we are left with. Here it's 2 plus 3n over n square. I can cancel out a 1n. So it's 3 over n plus 5 over n square. Here it's 1 plus 1 over n square. Now think about this. When n goes to infinity, 3 over n approaches to 0. Right, because that's a fraction, n gets large in the denominator, so overall it goes to 0. Same argument, 5 over n square approaches to 0. 1 over n square approaches to 0. Same arguments when n gets large. So what's left? In the numerator, it's 2 plus 0 plus 0, which is 2. In the denominator, 1 plus 0, which is 1. So the limit is 2. Convergence. So this is the proper way. Okay, this is the better way to find the limit. Okay, just factor out the highest degree term individually in both denominator and numerator. Okay, now you can use what I taught in the beginning as your scratch work to check your answer that you got here. Okay. Right, let me do one more example and finish this video. I know this video is already a little bit long, but I want to teach you something else. I will do more examples in future, okay, in the next video. But okay, think about this example. Now again, when you want to find the limit, factor out the highest term with the highest degree, highest power in numerator and denominator. Now you have to think about this highest power individually, right, separately. So in the numerator, the term with the highest power is 2n cube, so just take out n cube. So it's going to be 2 plus 1 over n cube. Okay, now in the denominator, don't try to take out a n cube because you took out a n cube in the numerator. No, you don't have to take out the same power. Okay, you just look at the denominator separately, look at n square plus 1, think what its higher power. Highest power is n square, so just take out n square. Okay, again I am saying, even though you took n cube in the numerator, that doesn't mean you have to take a n cube in the denominator. It doesn't need to be the same thing. It's just the highest power of numerator and denominator individually, separately. Okay, just like we look at the dominating terms individually in numerator and denominator. Okay, they doesn't need to be the same. All right, now simplify. N square and n cube cancel out, so what's left? You are left with the n in the numerator, right? That's fine. Now let's see what happens. So when n gets large, this term approaches to 0. 1 over n cube approaches to 0. 1 over n square approaches to 0. Okay, so let's see what happens. So the denominator, 1 plus 0, denominator is 1, but the numerator, when n gets large, this n gets large. There's no way around it. It goes to infinity. Infinity times 2 plus 0 is 2. I mean 2 plus 0 is 2. So 2 times infinity, it's infinity. So the limit is infinity. So this is a divergent example. Okay, right. Okay, great. Now I hope what I taught in this video is clear. We will do more examples in another video. So that will be a quick video where we just need to solve extra examples. Okay, in the next video let's look at another different type of sequence, and then after that next video we can do one video dedicated to doing some exercise from these type of sequences. Okay, all right, hopefully I'll catch you in the next video. Thank you.